Okay, so the recording is in progress. So Chris, please start.
Okay, thank you for inviting me to your seminar. So the main topic of today is our Mori dream spaces and their total coordinate rings or Cox rings. So I want to begin by recalling some basic facts about these spaces, a little background material. So for today, anyway, we're going to work over an algebraically closed field of characteristic 0. So you can see if you like. And a Mori dream space over such a field is going to be a projective normal variety. I'm going to let this denote its class group, and the class group will be assumed to be finitely generated. So not an elliptic curve, for example. And then for a choice of generators of the class group, the Cox ring is defined to be the sum of all of the spaces of sections of the divisors of represented by these generators. A different choice of generators will give an isomorphic ring like this, but we have to make a choice because section spaces are only defined up to isomorphism on a class. But this is the Cox ring, and it's in a sense the universal set of coordinates on the variety. In particular, any projective coordinate ring of the variety is a graded subring of this ring and can be obtained from this ring by taking invariance with respect to a certain torus. And so we say that this variety is a Mori dream space if this ring is finitely generated. So ultimately, a Mori dream space is a space that satisfies a finiteness condition. A priori, this ring could be infinitely generated. Its graded components could be supported on a convex cone that has an infinite number of sides, or various other aberrant behaviors could happen. But if we're talking about a Mori dream space, we're assuming that these things don't happen, and this potentially infinite object is actually described by a finite set of information. So if you have the Cox ring of a Mori dream space, in theory, you could email your best friend the information necessary to describe any coordinate system on that variety. So these spaces were first defined by Hu and Kiel in the context of the minimal model program. So, they have the property that all of their rational contractions can be understood combinatorially, essentially using variation of GIT. In particular, variation of geometric invariant theory by a torus. So the theory of Mori dream spaces and their Cox rings is very much intertwined with the representation theory and invariant theory of tori. So now I'll give you some examples of these spaces. So the quintessential example and the example that gives Cox rings their name are toric varieties. So before Mori dream spaces were named by Hu and Kiel, David Cox showed that toric varieties have a kind of universal coordinate ring, and that ring is always a polynomial ring on a number of variables equal to the number of rays of the fan that defines the toric variety. And this property actually characterizes characterizes toric varieties among Mori dream spaces as any Mori dream space whose Cox ring is a polynomial ring must be a toric variety. But there are plenty other ways to get Mori dream spaces. So smooth Fano varieties are Mori dream spaces. A very nice theorem of Okawa shows that the image of a Mori dream space is a Mori dream space. And a known theorem of Brion is that a wonderful variety of a connected reductive group is a Mori dream space. And there's a rich interaction between Mori dream spaces and representation theory. And so besides toric varieties, my favorite Mori dream spaces are flag varieties. And in that case, the Cox ring is just the Plücker algebra of the flag variety. And so in particular, to get the Cox ring of a flag variety, you sum up all of the irreducible representations corresponding to duals of dominant weights, which extend to characters on the parabolic, and the algebra of this Cox ring is given precisely by Cartan multiplication of representations. So these are very nice Mori dream spaces, and will come up later in this talk today. So on the other hand, there are ways to take perfectly reasonable Mori dream spaces and do perfectly reasonable things to them and get something that's not a Mori dream space. So the nicest toric variety one could hope for is a projective space. And a famous theorem of Castravet, Tevelev, and using work of Mukai shows that if you blow up projective space at n general points, so n points in very general position, then you get a Mori dream space if and only if a certain inequality is satisfied. And if you blow up too many points, you break the Mori dream space property. Also recently, a famous theorem of Castravet and Tevelev, which has then been sharpened by a number of authors, is that M0 n bar is not a Mori dream space for big N. So in particular, now I think the bound is down to 10. So if N is bigger than 10, then the moduli space, the Deligne-Mumford moduli of rational n-pointed curves is not a Mori dream space.
And for the smaller numbers, it's not known, or they are?
They are up to 7, I want to say, and then 8 and 9 are still unknown.
I see.
I think that's the state of the art. I might be wrong about that 7 though. Certainly 6 is. And then a nice another data point from this sort of corner of this theory is that Gonzales and Karu have shown that if you take certain toric surfaces, and I mean it's harder to imagine a nicer toric variety than a smooth toric surface. They've shown that for certain smooth toric surfaces, if you blow up the identity in the big torus inside the toric variety, or equivalently any sufficiently general point, then that might not be a Mori dream space anymore. So this theory is, intricately bound up with the theory of blowups and other symbolic operations that one can do on rings. And it's not always clear exactly what is making what go wrong. And so for that reason, it would be nice to have a large collection of well-behaved spaces which can be efficiently described by discrete data, which exhibit both behaviors, so that one could study the boundary between the Mori dream space side and the non-Mori dream space side. And the class of spaces I propose for this kind of study are toric vector bundles, or rather they're projectivizations. So a toric vector bundle is a vector bundle over a toric variety that is equipped with an additional action by the big torus of that toric variety. So not all vector bundles over toric varieties have such an action, but we're assuming that one exists. And this has the effect of discretizing and making the theory much more tractable for the geometry of these spaces. So when we take the projectivization of such a vector bundle, what we do is we go into every fiber of the vector bundle and replace it with a projective space, but sort of not the one you would immediately expect. You replace it with the projectivization of the dual of the fiber, and this is for technical reasons. It just makes certain equations look nicer, and this goes back to Hartshorn's paper describing basic properties of vector bundles over schemes, this kind of choice. So if you take a toric vector bundle and you projectivize it, you get a smooth projective variety. You can efficiently compute its Picard group. It's just the Picard group of the toric variety cross an additional copy of the integers. So the way you can read that equation is that any line bundle on the projectivization of a toric vector bundle is a pullback from the base, from the toric variety, possibly added with a copy of one of the Serre sheaves that you get for free by projectivizing a sheaf of graded algebras. So there's an O1 on the projectivization of a vector bundle, And the Picard group is ON for any integer n, plus a class pulled back from the base. So these are very nice varieties. And they were classified first in the 70s by Kaneyama, and then later in the 80s by Klyachko. And Klyachko's classification is very beautiful. It's by certain arrangements of subspaces in a vector space imagined as a fiber of the vector bundle. So the torus action allows one to characterize toric vector bundles with almost entirely discrete data. So a question that goes back to a paper of Milena Herring, Mustata, and Sam Payne is, are these spaces Mori dream spaces? And there's been some work on this. So one can show immediately that the answer is yes, if the bundle is a split bundle, that is, if it's the direct sum of a finite number of line bundles, because in that case, one can show that the projectivization is actually a toric variety, and those are known to be toric, or are known to be Mori dream spaces. So you can think of the projectivization of a toric vector bundle as something like a generalization of a Hertzebruch surface. Gonzalez then had the next relevant result. He showed that the answer is yes if the rank is very small. So if you take any rank 2 vector bundle over a smooth toric variety, smooth projective toric variety, you get a Mori dream space. And in fact, the resulting projectivizations are examples of something called complexity 1T varieties. They're very nice spaces, very close to being toric varieties. And then Jürgen Hausen and Heinrich Süß showed the answer is also yes, whenever you take the tangent bundle of a smooth toric variety, so a smooth projective toric variety. So, the tangent bundle automatically inherits an action by the big torus on the toric variety, which equips it with the structure of a toric vector bundle. And these are also very well behaved toric vector bundles. And once again, their projectivizations are indeed Mori dream spaces. Then the next sort of data point on this topic is a paper by Gonzales, Herring, Payne, and Süß, where they studied projectivizations of toric vector bundles via a certain quotient. So these quotients are close to, but aren't the same as geometric invariant theory quotients. They're called the maximal orbit quotient. And they showed that if the vector bundle satisfies some mild technical conditions, then the projectivization is a Mori dream space if and only if its maximal orbit quotient is a Mori dream space. So they did this by explicitly computing the Cox ring of the Mori dream space as a polynomial ring over the quotient. And then they showed that one can always find a toric variety with a toric vector bundle over it, where the quotient, the maximal orbit quotient of the projectivization of that toric vector bundle is actually one of these general blowups of projective space, like I mentioned a moment ago, constructed by Castravet and Tevelev. So that shows that there are toric vector bundles whose projectivizations are not Mori dream spaces. So something can go wrong, even though these varieties are sort of nice by every other measure. What I'm going to do now is explain
Chris, I'm sorry,
the method.
Can I say a few words? How do they prove that something is Mori dream space or not?
How do they prove it's not a Mori dream space?
Yeah.
Yes, right. So using this result at the bottom of this slide, they show that a projectivization of a toric vector bundle is a Mori dream space if and only if its maximal orbit quotient is. And they do this by explicitly computing the Cox ring of the bundle as a polynomial ring over the quotient. So, a finite polynomial ring over the quotient. So that shows that the Cox ring of the bundle is finitely generated if and only if the Cox ring of the quotient is finitely generated, right?
Okay, thank you.
And then they do some detailed work to construct a bundle whose quotient is this blow up. So there's actually a general story here that these bundle spaces, which I'll is the main point of my talk today, have a deep relationship with blowups of the fiber of the bundle. I won't talk about that, but that's sort of a thing that one can keep in their head in the background here. All right, so what I'm going to do next is describe a different point of view on toric vector bundles that gives a little bit more access to their Cox rings. So this is some work that's joint with Kumar's Castravet, and before I describe it, I'm going to give a little bit of background. I'm going to let L in a polynomial ring be a linear ideal. And then L defines a matroid on the set of parameters in the polynomial ring. And we're going to attach a finite polyhedral fan to this linear ideal called its tropical variety. And this is isomorphic to the Bergman fan of this matroid. If you've heard of tropical geometry before, this is one of the nicest possible cases of a tropical variety one could imagine. If you haven't, when you see trop L, you can think of a finite polyhedral fan. In this case, it's actually even a simplicial fan, and it's connected in codimension 1. So it's a very nice discrete object. It can always be realized as the support of a subfan of the Grobner fan of the ideal in question. And for today's talk, I want to highlight a certain set of substructures inside this tropical variety. So for every basis contained in this matroid, there's a distinguished subset of the tropical variety. It's actually isomorphic to a real space of dimension equal to the rank of the matroid, called an apartment. So for every basis, there's an apartment, and these apartments actually cover the tropical variety. And one can obtain a given apartment by intersecting the tropical variety with a certain face of the Grobner fan of the ideal. So this is a distinguished structure on this subfan of the Grobner fan that will be important for today. So here's an example of the sort of objects I'm talking about. If you take sort of the nicest linear ideal one could imagine, just this single linear form, a sum of 3 variables, that defines a linear ideal and a polynomial ring on 3 variables. And its tropical variety is this object. It's a union of 3 two-dimensional half spaces along a spine. And that spine is the line through the vector 1, 1, 1. And one can see 3 distinguished apartments inside this tropical variety, given by the 3 different ways to choose a basis among the parameters in this polynomial ring. So one could pick x0, x1, x0, x2, or x1, x2. And each such choice gives a pair of the pages of this fan, and that pair, when taken together, gives something that's homeomorphic to a 2-dimensional vector space. And I've highlighted here the apartment associated to the choice of the first 2 basis vectors. So that's the sort of picture one can keep in their head in the following discussion. So here is a tropical approach to characterizing or classifying toric vector bundles. So toric vector bundles over a fixed toric variety Y sigma can be captured by the data of a piecewise linear map from the support of the fan of that toric variety to a tropicalized linear space. That's the general theme here. So given a toric vector bundle, one can cook up a linear ideal L, in particular a matroid M sub L, and then the data of that vector bundle is captured in a piecewise linear map from the fan to this tropical variety, which is also a fan. So it's a map between fans. And this map satisfies a certain discrete continuity type condition. It says that if you take points that are close in the fan, in the sense that they live in a common face, then their image under this map also has to be close, in the sense that they have to live in a common apartment. So points in a common face have to map to a common apartment. They have to live together. And the information of such a map can always be captured just by the image of the rays, or in particular, the ray generators of the fan. So this is the idea. You take a vector bundle and replace it with a pair of data, a linear ideal and a map like this.
And sorry, here L is an arbitrary linear ideal, right?
L is linked intricately to the structure of E, but given a vector bundle, there is a computational way to produce L. Put it that way.
No, but if in the other direction, so if we have any linear ideal L and we have such a piecewise linear map, then
that defines a toric vector bundle. Yes.
For any L. Okay.
Yes.
Thanks.
So if you wanted to study all toric vector bundles, you could do it by studying all such maps to linear ideals.
And I'm sorry, but you will like provide the details or on the matroid and the other stuff, the Bergman family.
I was going to skip over the details for this talk, but I can say a few words about it.
Well, yeah.
In this case, the matroid emerges from actually I can add a page, can't I? The matroid ML is actually, you can always take a certain matroid studied by Hiroko Gabush Smith in their paper on Parliament polytopes, which is an invariant one can attach to a toric vector bundle. So that matroid always suffices. Another way to obtain this matroid is from Klyachko's description. One can show that given Klyachko's arrangement of subspaces of a vector space, that you can find a spanning set with the property that its intersection with any subspace is also a spanning set, and that would work as well. So those are two ways, of equivalent ways to produce L. So this description of toric vector bundles can be compared with a description of toric line bundles, which are, famously characterized by a piecewise linear map from the fan to the integers or Q, if you like. Was there a question?
No, I was sort of meaning the details concerning the previous page, probably.
This page?
No, the page before that, sorry. No.
Which? This
one
one?
more, this one. So yeah. So for instance, so like the way to define a matroid by a linear ideal is so you just sort of take the I suppose I can say that, but maybe it would be better if you could explain.
Yeah. Sure. So given L, right, in a polynomial ring, ML will be its underlying set will be this set of parameters, right?
Okay.
And then we say a subset S, right, is a circuit of the matroid.
Okay.
If and only if S is the support of some linear form in L. Equivalently, T is independent if and only if the vector space if and only if its image mod L is independent.
So you sort of, you take the linear space which generates the ideal, and then you consider each coordinate as a functional on the space, and you take the linear matroid.
Exactly.
Okay. Yeah. And then you use the term Bergman fan.
Yes.
What's that? This is the tropical variety.
If you're more familiar with tropical variety, then it's the tropical variety.
And what's a Bergman fan? In what generality is that defined? It's
defined for any matroid.
Okay, but you are not going to explain what it is.
Well, it's actually defined almost. It was defined before tropical varieties were, but it's defined in basically the same way.
Oh, okay.
You look at weightings of the elements of the matroid, which make two elements of any circuit equal and smallest. So it's the exact same way you would define the tropical variety.
Oh, I see. Okay.
Except it applies to a more general class of objects, right? Like possibly non-representable matroids.
And so an apartment is different from a maximal cone, or it's the same thing?
Oh, it's actually a union of maximal cones. So if we go to here, there are three maximal cones, right? And you can think of it as like pick a maximal face of the Grosvenor fan and intersect it with the tropical variety. And you'll get a collection of maximal cones of the tropical variety. And taken together, they make an apartment.
So that's precisely the definition. These apartments are parameterized by maximal cones, by initial monomial ideals.
Exactly. Yeah.
Okay. Thank you.
All right. Okay, so one immediate thing one can see from this kind of characterization of toric vector bundles is if this piecewise linear map has an image that lies in a single apartment of the tropicalized linear space, that's equivalent to the bundle being split. So one can think of, one can use some intuition from geometry here that if this image is very small, then the bundle has very good properties, and other properties emerge as the image gets spread out a little bit more. And then the fact that this is determined by that this map is determined by the image of the rays also allows you to think of the map as just a configuration of points on a tropicalized linear space. And so that leads to this slogan I have at the bottom: the toric vector bundles correspond to configurations on tropicalized linear spaces. So you can think of a sort of finite set of points moving around a fan, and each configuration defines a toric vector bundle. And you can ask, what properties of these configurations translate to amenable geometric properties of the bundle? Right. So here's an example of this characterization. If you take the configuration just given by the three coordinate directions in 3 space, that defines a configuration on this tropical variety we talked about a moment ago. And that configuration corresponds to the tangent bundle of P2. So the tangent bundle of P2 has, or P2 rather, has 3 rays. And so I need to tell you where each ray goes and send each ray to one of these 3 points. And that defines a toric vector bundle, and it happens to be isomorphic to the tangent bundle. But you could also think about these 3 points sort of, flying around these pages. And as you move the points, you get different toric vector bundles. And from the previous splitting theorem, you could think about if you took, say, 0, 0, 1 here and moved it into this line through 1, 1, 1, that would mean that the bundle splits. And you get a similar sort of stratified set of behaviors that can emerge from these vector bundles given this description. So this is a small example. So I'm going to make a further definition. Using this fact that the map is determined by the rays, we should just worry about the rays. So, given a piecewise linear map as before, I'm going to let D be called the diagram of the map, and it's just going to be a matrix whose rows are the images of the rays of the fan. So this is a matrix with n rows if you have n rays, and m columns if the size of the matroid is m. So it's an n by m matrix. And the sort of two criteria that our map needs to satisfy translates into two types of piecewise linear conditions that this matrix must satisfy. The rows that come from a common face need to land in a common apartment. That's a kind of piecewise linear condition that one can write down. And each row individually needs to be a point on this tropical variety, so it needs to satisfy the tropicalized linear equations that come from the ideal. So when you take these two conditions and put them together, as long as you select a matrix which satisfies them, you have the diagram of a toric vector bundle.
I'm sorry.
Yep.
So these maps, these piecewise linear maps, they are not like morphisms of fans in the sense.
No, they're not. They can fold the fan sigma in some funny looking ways, but they are piecewise linear in the sense that they are defined by, you know, m piecewise linear functions, right?
Okay. Okay, thanks.
Right. But when you solve both types of conditions, both the neighborhood condition and the tropical condition in n cross m space, you can prove that what you get is the support of a polyhedral fan. And then the integral points on this fan precisely represent toric vector bundles that can be characterized with, you know, whose linear space is this L. So I'm going to let delta sigma L be the set of integral points, you know, that satisfy these conditions. And once again, any matrix in delta sigma L now defines a toric vector bundle. And this is our discrete point of view on toric vector bundles. We want to think about choosing matrices in interesting ways, you know, that live inside of a fan like this, and try to translate their combinatorial properties to geometric properties of the vector bundle. So here are two examples of diagrams. The previous example tells us that the identity matrix lives in this delta P2 with this linear ideal x0 plus x1 plus x2. And that diagram defines the tangent bundle. And then here's a different, just another example. This matrix, this 4x4 matrix, defines a bundle over P1 cross P1. And it lives in the diagram associated to the linear form that you get by summing 4 variables together. Okay, so, you know, really there are exactly two conditions defining delta. There's a condition coming from the toric variety, and there's a condition coming from the ideal. All right, now what use is this? So in the next few slides, I'm going to tell you how one can give a description of the Cox ring of the projectivization of the bundle from this information. So it turns out that these Cox rings are examples of something of a general type of object called a Riesz algebra. So a Riesz algebra is obtained as follows. If you take an algebra over our field K, and you take a collection of integral filtrations, algebra filtrations, I'm going to define the associated Riesz algebra as you know, this sum here. It's a multigraded algebra over Z to the number of filtrations you took. And the rth piece of that multigraded algebra is obtained by taking, you know, the R1 part of the first filtration up to the Rn part of the nth filtration and intersecting them. And then one can show pretty easily that the multiplication operation on A endows this vector space with an algebra structure, and this is called the Riesz algebra. And so the kind of question we want to answer is, you know, if I make A a really nice algebra and G really nice integral filtrations, you know, when is the Riesz algebra finitely generated? And the answer is, as you would expect, not always. All right. So in this talk, we want to take some special integral filtrations. We want our integral filtrations to be controllable by discrete information, in particular by tropical information. So in this talk, we're always going to take our integral filtrations from what are called prime points in the tropical variety of an ideal, which defines A.
Yeah, I'm sorry, what are you going to be filtering? Which algebra?
So I'll unwrap that right now.
Oh,
so
okay.
I'm going to let A, be a domain that is presented by a polynomial ring using the ideal I. So given a presentation of a ring, that's the sort of information we're starting with. So we have a short exact sequence here of, of vector spaces. So a prime point will be a point on the tropical variety thought of as a point in the Grobner fan of the ideal, whose associated initial ideal is prime. That's the condition we want. So any point actually in the Grobner fan, but in particular a prime point, defines an integral filtration. So I should say we always want this to be, an integral point. I should say that. So this always lives in z to the m for us. So any prime point is going to define a z filtration of A by the following recipe. You take, I didn't write down that P of X needs to map to F. You take, for the rth filtration piece of the filtration defined by the prime point U, you take the image of all of the polynomials in the polynomial ring whose monomial terms have exponents which pair to a number bigger than or equal to R with our fixed prime point. So, if you want to know if your favorite element of your ring F is in GUR, you find a pre-image of F under this presentation. You look at the monomials that appear in that polynomial, and you take each of its exponents and take its inner product with U, which happens to be the right size to take inner product. And if you always get numbers bigger than or equal to R, you say that it's in that filtration piece.
So the associated graded is the quotient by...
That's right. So something I didn't write down here, but that's absolutely true. If you take the associated graded of this filtration, you get the polynomial ring modulo the initial ideal by U of this algebra.
So U is fixed, right?
U is a fixed thing, yeah. And in fact, we want to take a configuration of these U's. We want to fix U1 through Un, as in the bottom here, some configuration of points, prime points on the tropical variety.
Okay.
Then that will give the type of Riesz algebra we're interested in. So, you could imagine that these points, as they cross walls within the tropical variety or go from one prime cone to another, the behavior of the associated Riesz algebra might change. And you could ask, what kind of discrete structures on these configurations dictate the properties of the Riesz algebra? And then, most importantly, when is the Riesz algebra finitely generated?
I'm sorry, could I ask a sort of
yeah.
vaguely related question? So if I'm not mistaken, when you have a single filtration, the Riesz algebra, so its proj is a sort of flat family over
Yeah, that's right.
And when you have these multiple filtrations,
yes,
how should you think about that? So this proj, what kind of flat family does it define?
Right. So as you say, if you take a single filtration, it will always be and just because of the way we've chosen things, it will always have a finitely generated Riesz algebra. If you take the proj of the resulted graded ring, you get a partial completion of spec A by the spec of the initial, or rather the proj of the associated graded. If you just take the spec of that Riesz algebra, you'll get a flat family over A1 with general fiber spec A and special fiber the associated graded. If you take one of these fancier multigraded Riesz algebras, you can think about it as a flat family over affine space, if you'd like. And I propose that's a very useful way to think about it. One should think about it as a bundle, in fact, over affine space. And one should think of affine space as the spectrum of the Cox ring of a toric variety. But that's a quick way to imagine the spectrum of this Riesz algebra. It's a family over affine space rather than the affine line.
So, but like I was sort of asking about the fibers. So the generic fiber
is spec A. Generic fiber will be spec A, and then as you pass to the various coordinate hyperplanes and deeper into the coordinate subspaces, you get certain associated gradeds of A. You can think about it as taking, different combinations of the U and taking their the induced associated graded.
But like to take you will need some like monomial order to some semi-group order to take distinguish some associated graded. Would you not?
So yeah, this is partially where the this is a great question. This is partially where the aberrant behavior comes from, is that the U's might not all live in the same part of the Grosvenor fan. And so you'll need different symbolic elements to describe their associated gradeds. And sometimes you don't have a Grosvenor cone to use, and you get very strange behavior for that reason. And that's kind of exactly what goes wrong, is if these points are too spread out in relation to the Grosvenor fan, you get weird kind of metroidal interactions between the graded subspaces or between the filtered subspaces. And that's how infinite generation emerges. Mm-hmm. But on the other side of that comment is this remark at the top of the next slide. So just like we said before with split vector bundles, if you take your points sufficiently close together, that is, if they're all in the same face of the Grosvenor fan, then you can show pretty easily that the Riesz algebra is finitely generated. So that's a nice little toy theorem of this kind of topic. So the general theme here is, if your filtrations or your diagram or your prime points are all kind of close, finite generation is guaranteed, but as they spread out, you get emergent interactions which cause infinite generation. Okay, so here's the relationship with the Cox ring of a projectivized toric vector bundle. So I'm going to let sim E denote the quotient ring by this linear ideal. So take the vector space defined by the parameters and quotient by L and call that E, and then take the symmetric algebra over it. Then any diagram, just by construction, has rows in the tropical variety of L, and therefore defines one of these Riesz algebras that we're interested in. Every point in a tropicalized linear space is a prime point, and so it fits into the sort of restrictions that I've given on the previous slide. And we get this sort of symbolic object, this Riesz algebra determined by the diagram, and this sim E, which is ultimately just a polynomial ring. And then the proposition is that this Riesz algebra is always isomorphic to the Cox ring of the projectivized toric vector bundle. And so the problem of determining when the projectivized toric vector bundle is a Mori dream space amounts to determining when these sort of nicest possible Riesz algebras are finitely generated. So, on the previous slide, we took a general finite type domain and general prime points on its tropical variety. Now we've specialized to sort of what should be the nicest case, a polynomial ring and a collection of points on a tropicalized linear space for an ideal L which presents that polynomial ring. So a linear presentation of a polynomial ring. But even here we get bad behavior. So the question has now become, when does a diagram in our fan of diagrams give a finitely generated Riesz algebra? And I'm also very interested in understanding, what kind of set do these diagrams make? This set must have some kind of, or maybe it doesn't have some kind of geometry. Is it really aberrant and terrible? Is it some sort of fractal set inside this fan? Or is it polyhedral and sort of well behaved in the ways we expect from symbolic computational algebra? So that's the question I'd like to at least partially get towards answering.
I'm sorry, maybe I sort of missed the main point here, but this Riesz algebra defined by E and D.
Yeah.
Did you actually define it, or should we?
It's this Riesz algebra. So take for your filtrations the prime point filtrations defined by the rows of the diagram, and take for your algebra just the polynomial ring.
Okay, the rows of, okay, yeah, I get it now.
Right.
Thanks.
And so once again, this could be considered sort of the tamest possible instance of one of these Riesz algebras, right? Okay, so now I'm going to start telling you about some of our results. So the first pass at this problem is that we can define an algorithm which, roughly speaking, finds a finite generating set of the Riesz algebra if one exists. So it could be that this Riesz algebra is very much not finitely generated, in which case this algorithm runs forever. But if it is finitely generated, then it can take as input any generating set of this symmetric algebra on E, and it turns a few times and cooks up a generating set of the Riesz algebra, rather or equal to, or the Cox ring, however you want to look at it. So if it's finite, we can find the generating set in a procedural way. That's the point. And so as an example of what this looks like, if we start with this bundle H, which I told you about a few slides ago with this 4x4 diagram over P1 cross P1, it turns out that W0, W1, W2, and W3 do not suffice to generate the Riesz algebra, but after 2 turns of the algorithm, we can introduce 2 more generators which do. And it expands the diagram to this 4x6 integral matrix and adds 2 more columns. So this algorithm, will find the generating set if there's one defined. And the generating set will not always be linear. It could be polynomial in higher degree, but it can find it. And we have several examples in the paper of this happening. This isn't very satisfactory because, of course, having a generating set that has 7 trillion elements in it is about on the same level as having an infinite generating set for humans at this point. So we might not, we might have a situation where we have a Mori dream space, but effectively we don't know because, because of the limitations of computation. So it would be nice to have a characterization of when the algorithm stops, and we have something to that effect. So this theorem is a little complicated to say, but the main point is, I'll describe it in a moment, but the main point is that if the prime points we started with lift to prime points on another ideal, that's exactly when it terminates. So here's the characterization of this behavior. So I'm going to let A be as before. It's a quotient of a polynomial ring by an ideal. And I'm going to let U be a configuration of prime points on the tropical variety of that ideal. So what you do is you take your n elements from this configuration and think of them as the rows of a matrix, like we've been doing with the diagram. And then you look at the columns of that matrix. And then you let the parameters x1 through xm, be this generating set B in your algebra. And then finally, we're going to define an ideal in a polynomial ring as follows. So script di will be the kernel of a distinguished map phi. And this map is defined as follows. You send z1 through zn to the inverse of a Laurent polynomial generator in the Laurent ring with n generators over A. And you send these y's to the generators that you started with above, appropriately homogenized by the columns of this matrix. So that's the map. You send the z's to Laurent polynomial elements, and you send the y's to homogenized generators. All right. So this is a ring map. If A is finite type, then this is something you could put into Macaulay too. And then what we're going to do is we're going to take each of these prime points from the configuration and pad them with zeros to get new points, u tilde. And these u tilde always end up living on the tropical variety of the kernel of this map. And then this is the characterization of the stopping condition. The image of this map is the Riesz algebra. In particular, the Riesz algebra is finitely generated by the generators you started with, if and only if each of these padded u points are prime points. So this is a big mouthful of a statement, but ultimately all of this can be checked in Macaulay 2. You start with a configuration of prime points, you lift them in a canonical way to the tropical variety of the kernel of this map, and then you can ask, are these prime points on this bigger ideal? And if they all are, that is equivalent to the Riesz algebra being finitely generated. All right, so now we can use this characterization to come up with some large families of Mori dream space bundles. That's sort of the purpose. Before I describe those families, though, I want to describe a quick geometric application. So anytime you blow up a toric variety along a ray, you take the ray and it lives in some face of the toric variety, and you triangulate that face and you get a new toric variety with a blown down map to your original toric variety. So anytime we have an operation like this, we can consider the pullback bundle under the blow up. And a natural question is, if you have a Mori dream space bundle on Y sigma, when is its pullback a Mori dream space bundle on the blow up? And given this previous theorem, we have a natural characterization of when that happens. So there's always a linear surjective map from this big tropical variety of scripty I to trop L. And you can take the collection of prime points in trop I, which form a finite polyhedral subcomplex of the tropical variety, and you can push it forward by this map, and you get a polyhedral complex in the support of the tropicalized linear space, and I'm going to call that tau. So this is some distinguished subspace of the tropicalized linear space. Then if you blow up the toric variety along array rho, you know that the pullback of your bundle is also a Mori dream space whenever phi of rho is contained in this complex tau. So this is a piecewise linear condition on the blow-up ray that one can apply to check if the blow-up bundle is also a Mori dream space. So that is an illustration of how sort of these piecewise linear and discrete techniques can tell us things about the geometry. Okay, so now I want to tell you about a few families of distinguished Mori dream space bundles that emerge from this theory. So I'm going to fix a linear ideal L and a fan sigma. Then I'm going to say that a diagram defines a formal bundle if the associated map phi from a few slides ago and it has a complete intersection as a kernel. That is the scripty I ideal is generated exactly by the codimension number of generators. So these are the complete intersection Cox rings that emerge from this theory. And if you like, the way you could think about the generators of this ideal then is the way you obtain them is you pick a specific collection of generators of the linear ideal and you homogenize them. So any formal bundle has an ideal presented by the appropriate homogenizations of some generators of the linear ideal. And then one can prove that if you select your favorite generators, then the space of diagrams which are formal with respect to those generators form a finite locally closed polyhedral subcomplex of the fan of diagrams. So this is a baby case of the kind of discreteness we would hope holds in general. That there is some subfan of this fan, and whenever you pick a diagram from that subfan, something very nice happens. You get a very specific, complete intersection presenting the Cox ring. In particular, the Cox ring is finitely generated. So this subcomplex has some nice properties. First of all, it always contains certain points, which I'll tell you about. And second of all, when the linear ideal is especially nice, its description is especially nice. So those can be viewed as sort of two extremal cases of this theory. One is where you make the diagram very simple, and the other is where you make the linear ideal very simple. So when the diagram is simple, we call the bundles sparse bundles. So roughly speaking, sparse bundles are bundles whose diagrams look like this picture right here. All of their rows have at most one non-zero entry, and that non-zero entry is positive. So whenever that happens, we say the diagram is sparse. And then I'm just noting here that you actually get the same bundle if you add a uniform integer to each row, to every position in a given row. So if we take a row and we add 1 to every entry in it, that defines the same projectivized toric vector bundle. It's actually the discrete version of tensoring that vector bundle by a line bundle. So I'm also going to say that a diagram is sparse if its diagram can be brought to this form at the bottom of this slide by that operation. So it turns out these diagrams are always in this distinguished subcomplex and therefore always define Mori dream spaces. So anytime you take a diagram that, most of the entries are 0, it's a Mori dream space. So these sparse bundles were, some of them anyway, a certain subclass of them were known already to Gonzales, Herring, Payne, and Seuss, and also Nodland by a different description. The geometry of the projectivizations of these bundles is always very nice. They always form something called an arrangement variety, which have been studied recently by Hausen, Hische, and Robel. And these, the scripty ideal of the Cox rings of these bundles always has a very nice condition. Every point on its tropical variety is prime. So these form something called a well-poised T variety, which just means every point on the tropical variety is prime. And so in particular, these projectivized toric vector bundles have a large class of combinatorially controlled toric degenerations and Newton-Kunkov bodies. And using this previous result about blowups, another thing you can conclude about them is any pullback along a toric blowup of a sparse bundle is also a Mori dream space. So this is the class of bundles you get when you make the diagram especially simple. There's another class of bundles you get when you make the linear ideal especially simple. So I'm going to say a bundle is a uniform bundle if the linear ideal is very general. That is, if its associated matroid is a uniform matroid. So you can think about this as that the linear ideal is generated by the rows of a matrix where every minor is non-zero. So if that happens, we say it's a uniform bundle. It turns out in this case, the subcomplex F sub L can be completely characterized by a condition. I'm not going to write it down, but it's basically certain arrangements of zeros appear in the diagram. So the story here is if you pick your favorite uniform matroid and then you write down any integral matrix where the zeros are in the right places, you get a Mori dream space. So as an example of that, here is a hypersurface Mori dream space. And in this case, in this sort of small case, the zero condition is just that every 2 rows share a 0 entry. So whenever that happens with a hypersurface, you have a Mori dream space. And so I'm going to leave the projectivized toric vector bundle portion of the talk with this question. We have sort of some large families of Mori dream spaces to explore and some symbolic algebra techniques to explore them with. And so we could ask some questions. Vector bundles don't just define nice spaces, they also come with some algebraic operations on them. In particular, for any two vector bundles, you can take their direct sum and you can take their tensor product. And so we could ask, given two Mori dream space bundles, is their sum a Mori dream space bundle? And is their tensor product a Mori dream space bundle? So are there any questions before I move to the next portion of the talk? Am I still here?
Yeah, you are.
Okay, good. Okay. So projectivized toric vector bundles could be viewed as sort of the nicest case in a broader construction. Instead of making every fiber a projective space, we could consider other spaces. So for the remainder of the talk, I'm going to consider what happens when, instead of taking bundles in projective spaces, we take bundles in flag varieties. So these are called flag bundles. And one could think about this as, in some sense, what we're talking about are going to be multi-Riesz algebras of Plücker algebras instead of multi-Riesz algebras of polynomial rings. But in some sense, the same theory applies. So I want to consider bundles of the following form. We take a G principal bundle for our favorite connected reductive group over K, and we pick our favorite parabolic subgroup of that group, and then we take a quotient on by this parabolic. So if you recall, a principal bundle is a bundle over the space where every fiber is isomorphic to the group, and there's an action by the group on the bundle. So a toric principal bundle is defined in exactly the expected way. You have a principal bundle over a toric variety, which also has an additional action by the big torus that commutes with G. So one could think about taking such a space and quotienting by this parabolic, and then every fiber of the resulting space will be the flag variety of G by that parabolic. So if the base toric variety is smooth and projective, then the resulting quotient is also smooth and projective. And the Picard group, just as in the case of a projectivized toric vector bundle, is straightforward to compute. It's just the product of the Picard group of the toric variety with the Picard group of the flag variety. So this is, an equally well understood object, just like a projectivized toric vector bundle. And, we could ask in the same sense, starting with a Mori dream space, or when is such a thing a Mori dream space? So principal bundles, toric principal bundles end up having a nice combinatorial classification, just like toric vector bundles do. Only the role of the tropicalized linear space is exchanged out for a richer combinatorial object called a building. So the spherical building associated to a group, I'm not going to define it in detail, but it is a polyhedral, it's a simplicial complex, in fact, which can be expressed as the union of certain distinguished subcomplexes associated to the Cartan subgroups of G. And these fit together as the one parameter subgroups of G fit together. And these subcomplexes are called apartments. So if you've never studied or heard of buildings before, you can imagine a kind of infinite version of a tropicalized linear space. Instead of considering the apartment itself, I'm going to consider the cone over the apartment, just because it makes the theorem work. So in this case, instead of a simplicial complex, it's a complex of simplicial cones. And here is the theorem which plays the same role that classifying toric vector bundles does. So a toric principal bundle for a group G can be completely characterized by a piecewise linear map from the fan to this cone over the spherical building with an additional combinatorial continuity condition. That is, anytime 2 points are close in the fan, in the sense that they live in the same face. Their image is close in the building in the sense that it lives in the same apartment. So this is, somewhat more complicated because of the involvement of spherical buildings, but it's in complete analogy with the toric vector bundle case. And we can do similar things at this kind of characterization. So a natural question is, given...
There, and then this theorem is said framed?
Yes, so framed is a technical addition where what we're saying is we're picking the fiber over a particular point, the identity in the torus, and we're fixing an isomorphism with the group. So, a framing, if you will.
Okay.
Think about it like choosing a basis somewhere. And we need to do that to make the theorem true. Right. But, given a toric principal bundle, you can choose a framing. So here's then the question. Given a piecewise linear map, which once again, you could think of in analogy with giving a configuration of points on the tropicalized linear space, when is the associated flag bundle, or when are the associated flag bundles Mori dream spaces for the various parabolic subgroups Q? And as you would expect, there's sort of a closeness condition which guarantees it. The sort of toy theorem you would want to begin with works. So if you take a smooth projective toric variety and you fix one of these maps and look at the associated principal bundle, then if the image of the map lies in a single apartment, that is, if the entire image of the map is all bundled up and close together, then all of the associated flag bundles are Mori dream spaces. So this is, once again, is just a toy result that illustrates the principle at work here. We can also worry, so the remainder of the talk will be about the special case when we look at the what's called the frame bundle of a toric vector bundle. So the frame bundle can be thought of as just tensoring the toric vector bundle with a copy of a vector space of the same of dimension equal to the rank. And it's also like looking at all of the possible framings of the fibers of the toric vector bundle. So all the choices of bases in each fiber knit together to also form a bundle, and it's a GL principal bundle, where GLR, where R is the rank. So just fixing some notation here, I'm going to let I be a tuple, which gives you dimensions of a model flag. And I'm going to let FLI be the flag variety of all flags with that dimension vector. And I'm going to let just FL with no subscript denote the full flag variety. Then for a toric vector bundle, or in general a vector bundle, and one of these flag dimension vectors, I'm going to let FLI of the vector bundle be the associated flag bundle. So, if you like, you can construct this by making the frame bundle and then quotienting by the appropriate parabolic. And you can also think about it as going in and replacing each fiber of the vector bundle with the corresponding flag variety of that fiber. So these have popped up recently in a few places. They're also known out there as relative flag varieties. And relative flag varieties and relative Richardson varieties over, say, Jacobians have been studied recently in Brill-Noether theory. But I'm going to focus on the case where of relative flag varieties, or flag bundles rather, over toric varieties, where we can say some things. So the question is, when does a relative flag variety have a finitely generated Cox ring? So, given a toric vector bundle, when is FLI of that toric vector bundle a Mori dream space? So this is true by the previous apartment theorem if the toric vector bundle is split, because in that case, the piecewise linear map corresponds with the map to the tropicalized linear space. And you can show that that actually gives a map to a building that lands in a single apartment. The word apartment was used earlier intentionally. And you could ask, sort of refinement of this question, what if you start with a projectivized toric vector bundle that is a Mori dream space, like one of the examples we looked at earlier, then are the flag varieties Mori dream spaces? And immediately the answer is no. So a counter example can be provided by something Gonzales, Herring, Payne, and Seuss constructed when they were analyzing toric vector bundles. So they showed the existence of a toric threefold, so a three-dimensional smooth projective toric variety, whose tangent bundle is obviously a Mori regime space bundle by Hausen and Souza's result, but the cotangent bundle is not. So in other words, if you projectivize the cotangent bundle, you get what's something that's actually isomorphic to the Grassmannian of two planes bundle of the tangent bundle, and that is not a Mori dream space. And that also implies that the full flag bundle is not a Mori dream space by Okawa's theorem, if you'd like. So it's possible to find a rather small, smooth projective example where this falls apart.
Okawa's theorem is the one that said about images?
Yes. So
Okay.
any smaller flag bundle is the image of the full flag
Yeah, it
bundle.
makes sense, right?
Right. Just in the exact same way that it happens with flag varieties, right?
And which is it hard to say which sort of polytope, this three-dimensional polytope?
Yeah, it's a little involved. It's a repeated blow up of projective space, though.
Okay.
In fact, I think it may be a step on the way to Kapranov's blow up of projective space, but I'm not sure.
Okay.
Yeah. So here, though, is a result that links positive answers for flag bundles with a positive answer for this question about sums of toric vector bundles that I mentioned earlier. And it's actually it's a rather straightforward theorem to prove, but it still has a number of very nice consequences. So if you take a toric vector bundle, then the following are equivalent. The tensor product with a vector space V, or in other words, a dim V sum of these toric vector bundles, the toric vector bundle with itself, has a Mori dream space projectivization if and only if the flag bundles for every index set I whose maximum is less than or equal to the dimension of this vector space is a Mori dream space. So it's the if and only if that is really nice here. So one direction is, once again, one implies two, once again by Okawa's theorem. Two implies one is a close computation of the effective cone of the flag bundle coupled with some mild invariant theory. But these two facts still end up being equivalent. And so finding sums of toric vector bundles that are still Mori dream space bundles is in some way linked at the hip to finding full flag bundles that are, or flag bundles that are Mori dream spaces. So here are some corollaries of this. I mean, it maybe even shouldn't be a theorem, it should maybe be an observation, but here are some nice corollaries of this observation. So if the full flag bundle of a toric vector bundle is a Mori dream space, then the tensor product with any vector space is a Mori dream space bundle. So this is immediately a infinite collection of arbitrarily high rank toric vector bundles whose projectivizations are also Mori dream spaces. Another corollary is that the counterexample of Gonzales, Herring, Payne, and Seuss implies that there is a toric vector bundle out there, namely the tangent bundle of this toric threefold, where its projectivization is a Mori dream space, but its sum with itself is not. So this is a negative answer to the sum question and a negative answer to the tensor product question, as E plus E is the tensor product of E with, the two-dimensional vector space. Another consequence that just follows from the logic is that if a full flag bundle is a Mori dream space, then the full flag bundle of any sum with itself an arbitrary number of times is a Mori dream space. And so applying this to Gonzales's result on rank 2 bundles shows that any sum of a rank 2 bundle with itself an arbitrary number of times and any flag bundle of such a sum is always a Mori dream space. So that's fun. And here's what we get, or a diagram that illustrates some consequences of what we get when we apply these constructions to the examples of Mori dream spaces I talked about earlier from the projectivized vector bundle Mori dream spaces I talked about earlier. So if we put both niceness conditions on the toric vector bundles, if we make them both sparse, where the rows of the diagram have at most one non-zero entry, and uniform, where the matroid is a uniform bundle, then we get a nice infinite family of examples of these Mori dream space toric vector, Mori dream space flag bundles. So the way you should read this diagram is every dot represents a uniform matroid of size M and rank R, where R and M are the coordinates. And every dot to the right of one of these lines has the property that certain collections of flag bundles are Mori dream spaces. So everything to the right of the orange 2 line has its Grassmannian of 2 planes bundle, a Mori dream space. Every point to the right of the red 3 line has its Grassmannian of 2 plane and Grassmannian of 3 plane and its 2-3 flag bundle, a Mori dream space, and so on. And these lines form an infinite family that kind of coalesces to the line y equals x. And in particular, every dot along the sort of the super diagonal here, which correspond to the hypersurface bundles, have full flag bundles that are Mori dream spaces. So an example of one of those is the tangent bundle of a projective space. So the full flag bundle of the tangent bundle of projective space and many other hypersurface bundles are always Mori dream spaces from this sort of invariant theory technology. All right, so we know that there are bundles out there which give full flag bundle Mori dream spaces. And as a consequence of that first corollary, we get an infinite family of finitely generated Cox rings. For every L bigger than or equal to 1, we get that the Cox ring of the projectivization of the L-fold sum of the bundle with itself has a Mori dream space, and so it has a finitely generated Cox ring. And we could ask, are these Cox rings related in some natural way? In particular, what algebraic properties of these Cox rings hold independent of this parameter L? Do their presentations stabilize at some point? Do their Betty numbers stabilize at some point, and so on? Like, what uniformity arises out of this family independent of the indexing parameter? And this question belongs to the theory of representation stability. So a sort of model theorem from representation stability is this classical invariant theorem of Wiles. So if you take a finite dimensional representation of a group, then if you sum that representation with itself a number of times equal to its dimension, and take the invariance in the associated polynomial ring, if that invariant ring is generated in degree n, so is every other invariant ring of every other L-fold sum of the representation. So that's a very nice classical theorem of Wiles. It's been proven in a dozen different ways at this point, but that's the kind of theorem we want to imitate with these Cox rings. So, we want, maybe in some abstract sense, a representation of the group gamma is something like a vector bundle over the stack point mod gamma. And maybe an analog of Wiles' theorem holds for that reason, as we're also studying vector bundles over a nice object. So here's
a question. In this Wiles theorem, is there any condition on D?
On D?
Yes, so this D-dimensional representation of the group gamma, so it holds for any representation. Yeah, no condition on the representation.
Yeah, you'll notice that the statement is conditional, right? It says that if that guy is generated in degree n, then the second guy for any L is generated in degree n. So it entirely could be the case that, it's not even finitely generated.
Oh.
Right. But his theorem says if you find generators and they're all of degree n or less for this D-fold polynomial ring, the invariant ring in this D-fold polynomial ring, the same degree will suffice for any other of the rings you'd want to make, right?
Okay, I've got it. Yeah, thank you.
And so the second theorem I want to tell you about is that analog of Wiles' theorem holds precisely. And the way to say it in the language of this topic of representation stability is that the functor that you get by sending a finite dimensional vector space V to the Cox ring of the projectivization of E tensor V is what we call a bounded twisted commutative algebra. So twisted commutative algebras are functors from finite dimensional vector spaces to rings. And Stephen Sam and Andrew Snowden have a rich theory of these functors, which says that you can treat them roughly as you treat finite, algebras of finite type. And you can prove similar properties hold for these functors that would hold for a single algebra of finite type. And this theory of twisted commutative algebras is a framework in which to prove that certain properties hold irrespective of an indexing parameter or the indexing vector space. And so the theorem in particular is that if the rank of the vector bundle is R, then if the Cox ring of the R-fold sum is generated in degree n, then so is the Cox ring of every other sum of the vector bundle. So in particular, the generating degree stabilizes after the R-fold sum. It can actually jump quite dramatically at R, but after that, it does not change anymore. So I'm going to say from now on that this functor is I'm going to call it a twisted Cox ring of the projectivized vector bundle. And a remark, this boundedness is a technical condition that comes from this theory of twisted commutative algebras. It says if you look at the representations of GLV, as a function of V that appear in the Cox ring, that they stop at a certain point, that they correspond to Young tableau with number of rows that terminates at a certain point. They never grow beyond a certain level. And that's what bounded means. So this, the Cox ring, the twisted Cox ring of a vector bundle is bounded, but it turns out that the twisted Cox ring of a full flag bundle is not, even when it is still finitely generated for all V. So this bounded condition is something more than saying that it's finitely generated for each instance. It actually means that there's some uniformity to it. And so with that in mind, I'm gonna make a definition here and ask some questions about it, and that'll be the end of the talk. So I'm gonna say that a twisted commutative algebra is polynomial if it can be expressed as the following type of functor. Send V to f of V for some functor of finite that takes a finite dimensional vector space to another finite dimensional vector space, and then take sim of the image of that functor. So one could think about this as like the potential polynomial rings in the world of twisted commutative algebras. Then given a twisted commutative algebra, you could ask if it has a presentation by a twisted polynomial algebra. And what would that be? That would be an exact sequence of this form that's natural, and an exact sequence of natural transformations of these functors. And if even better, it would be great if you could find another polynomial functor from V to finite dimensional vector spaces, which effectively always gives the generating set of the presenting ideal here. So this is something like asking for the ideal of relations for a twisted commutative algebra, if it exists. And so my twofold questions that I don't know how to answer are, given a rank 2 bundle, can we always compute a presentation like this for its twisted Cox ring? We know its twisted Cox ring is always finite, is always bounded because of the theorem earlier, but can we actually give the defining relations as a functorial image of the input vector space V? And the second question is, can we do the same thing for a sufficiently nice toric vector bundle? We know that this doesn't always work for toric vector bundles because their full flag varieties aren't always Mori dream spaces, but for a nice one, can we find a twisted commutative presentation of the twisted Cox ring of its tangent bundle? And so I'll finish with this slide where the answer is yes, and here's how you do it for the nicest of possible smooth toric varieties, projective space, right? The best one. So this is a theorem of myself and my graduate student, Courtney George. I'm going to let T sub n denote the tangent bundle of Pn. Then the twisted Cox ring of the tangent bundle of Tn has the following presentation. You take the input vector space V, you add one line to it, K, then you tensor that with K to the n plus 1, and then you add the nth exterior power to V to that. And then you take the symmetric algebra. So you'll notice that each of those operations is functorial in V. So that is a twisted polynomial functor. And then we can show that that twisted polynomial ring always surjects onto the twisted Cox ring of the tangent bundle of Pn. And we can also explicitly describe the ideal. I didn't write it out here, but it is a certain multi-parameter flat deformation of a Zelevinsky quiver ideal. So Zelevinsky quiver ideals, there's a beautiful theory of them. You can read about it in, for example, Miller and Sturmfell's book on combinatorial commutative algebra. So if you take the following quiver variety defined by this short little sequence here from a line to an n plus 1 dimensional vector space and then to our target vector space V, and that if you demand that the second morphism always has rank less than n, and you demand that the composition of the two morphisms always has rank 0, then you get a certain, Zelevinsky tells you how to form a certain ideal that's always a prime Cohen-Macaulay ideal. And our ideal here, I(n) sub V, is a straightforward deformation of that ideal. So in particular, this Cox ring is always a Cohen-Macaulay ring, and in fact, it's always a Gorenstein ring. And so I'll finish with that. Thank you for listening.
Thank you, Chris. Questions?
So how explicitly the ideal is described in this last part? So I mean, do you give explicit relations or?
Yeah. So there are, you write down certain quadratic forms and certain like polynomials and determinate minors. But we can write down precisely what they are. They're all integral over Z, for example. We can say that.
Okay, I see. And well, I mean, how much does it depend on n? So is the structure kind of more or less the same for different n, or?
It is. It's like you take certain n by n minors and set them equal to a linear form times one of these exterior power parameters.
Okay.
And then the other thing you do is you take certain quadratic forms in the k to the n plus 1 and the v terms. So I mean, but they're the same. They're uniform for all n as well. But I am pretty sure that this is not, so kind of interesting. I'm pretty sure, I haven't checked it, but I'm pretty sure it is not a like bifunctor in the projective space entry and V. It's only, I think, a functor in V.
I see.
But like for example, it's always presented by generators in degree 1 and n. You can say that, and its relations are always, I guess, degree n in those generators at most. I'm sorry, I cut somebody off.
No, I had a meta question. So in the first two parts of the talk, you quoted some paper with Castravet several times. Is that
yes.
Is that something that's already on the archive, or?
It's on the archive. I think it has a title like the toric vector bundles and piecewise linear geometry or something like this. I can find it.
How? I'm just trying to find it. How old is it? It's 2019?
2019, yes.
Okay, yeah. Toric flat families, valuations, and tropical geometry over the semi-field of piecewise linear functions.
Yes.
Yeah. Okay, that's the one. Thanks. All the reference were to this specific paper.
Yes.
The references with Kave.
Yes.
Great.
Yeah, it's archive number 1907.00543.
Yeah. And this result with your student, this is
we're hoping to have it on the archive in the next few weeks.
okay.
Good. Any further questions? Okay, so seems not to be the case. So Chris, thank you very much for your talk.
Thank you for having me.
Let me stop the recording.